Okay, all right, let's start. So hopefully we'll finish with our discussion related to differential amplifiers. And there's a lot to discuss, but we are short on time, so let's wind up. If you recall, last lecture, I was telling you that if I look at common emitter amplifier, and we recognize that in a simple common emitter amplifier, the gain will always be less than ICQ RC by VT when there's a resistive load. And this puts a constraint on how large a gain you can get for a given supply voltage, because ICQ RC always has to be less than the supply voltage here. And as a solution to that problem, we said, well, we can take this common emitter amplifier, take the resistive biasing here, take it out and replace it by an active load. And when we do that, then the gain does not really depend on VCC as long as you ensure that the two transistors are in active mode. The gain does not depend on the supply voltage anymore, and you're able to get very large gain very large gain. And it's also, you can see it's independent of current, it's independent of supply voltage. And so it's a nice circuit. And along the same direction, then we said, when we look at a differential pair, and differential pair is also, when you look at it in the differential mode part, it also gives you a gain which is GMRC. And if you're not happy with that particular gain, one can take this RC out and one can replace it by an active load. So it's the same principle that we apply here also. Take the resistive biasing here, collector resistance, and replace it by two PNP transistors which act as active load here. And I was telling you that the problem with this particular circuit is biasing. As an example, we showed in the last lecture through simulations that when you have, let's say you bias it at 2 milliamperes, so this part is biased properly, and we have to bias the PNP also. So let's say if I put 5.3, ensuring that there is 0.7 volt across the emitter base voltage here, what I end up getting is 5.9 and 5.9. The transistors are in saturation, and these are of course in the linear region here. On the other hand, if I put a little bit higher, 5.31, what I end up getting minus 0.65 here. These transistors go into saturation, and these are fine. So the biasing is extremely sensitive to what you apply here, and it becomes difficult to find a voltage such that both the transistors are in linear mode. Alright, so this we had seen earlier. The solution to that particular problem, one solution is that instead of using active load in this manner here, what you do is you take this particular part here, connect it to the collector. So base and collector of Q3 are shorted together, and you end up with a configuration which we call as a current mirror. So instead of a normal active load, we have a current mirror load here. Differential amplifier with current mirror load. And we had shown in the last lecture that biasing is very stable now. Okay, as an example. And we had seen several other things. We had seen that this circuit compared to here provides you with higher differential gain, lower common mode gain, and biasing is more stable. So we'll see this in more detail today. Anyway, as with respect to biasing, for example, the same 2 milliamperes here, when we when we short the base and collector, make it a current mirror, is 11.3, 10.26. All the transistors are in linear region. To ensure that the biasing is stable, let me change the supply voltage to 12.5. 12.5. Still, all the transistors are in linear mode. All right, so all the transistors stay in linear mode when I change my, as an example, supply voltage, and your circuit works fine. All right, so I'm not going to spend time on this. So let's look at the differential mode part here. Now, differential mode analysis, now you'll see these analyses are, so we have in differential mode, I've removed the supply, put it to ground here, and note that what I've done is this current source that you see here, we normally implement using a transistor. So I put a transistor's resistance here, R05. So assume that there is a Q5 connected here, Q5 for biasing, and the output resistance of Q5 is R05. For differential mode, we put 0.5 VID here, minus 0.5 VID here, and we need to find out what the value of this particular node is. So let's what the ratios are. So let's go forward. So one of the strategies that you can use, which is very useful for analysis, is instead of taking a circuit like this and directly finding out what is V0 by VID, differential mode gain, which you can do that, but it's complicated. One of the ways of doing it is wherever you have to find the gain, whichever point you're looking for, and you have to find the gain. So I want to find the gain at this particular point. What you do is you build a Norton's equivalent circuit at that particular point. So Norton's equivalent circuit would require you to find a Norton's current, IN. So in order to find Norton's current, you always take that particular node, short it to ground, and you find out how much current is flowing there. That gives you the Norton's current. And Norton's resistance, we know, is the resistance looking from, when you look left, what is the overall resistance that you see there. The analysis becomes much simpler when you break it down into these two parts. Calculation of Norton's current and calculations of Norton resistance. So break it into two parts here, okay? So that's what we are doing. We're calculating what is the Norton's current here, and then we'll calculate what is the Norton's resistance looking from here. So the whole differential amplifier will become what? A Norton's current in parallel with a Norton resistance. The whole circuit becomes like that, and then it's very easy to write down the gain. Okay? So this becomes much simpler. So let's calculate what is IN. So now, again, the analysis is, you can see here Q1, Q2, they are coupled to each other. And unlike the previous case, where what happened was the circuit was symmetric. In the previous case, the circuit was symmetrical. Both sides were, the left half and the right half were identical. And we could say, even now we'll do that, but we could say easily that this point was ground. This point was a small signal ground here. Now you can see there's no symmetry. At least when you look at it, this side is connected here and this side is connected here. So there's no direct symmetry. But note, if you look at this particular picture here, this point is of course small signal ground. We have put it to ground. Now if I look at this particular node here, at this node here, what is connected between this node and ground? A transistor Q3 whose base and collector are shorted together. So when I look at it from between here and ground, what do I see? 1 over GM3. Whenever you have a transistor with its base and collector shorted together, effectively it's a resistance which is 1 over GM. So between this node and ground, I have 1 over GM. And 1 over GM is what? It's a very small resistance. So whenever you have a very small resistance, what is the value of the voltage that will develop here? See, current is flowing through the resistor. So I'll have a value of voltage. But if the resistor is very small, the value of the voltage will be very small. All right. So our assumption is that this voltage at this particular point will be very small. Very small means that this node is very close to ground. Very close to ground. All right. So if you make that assumption that this node is very close to ground and this is of course ground, then you look below this particular plane here. You look below this particular plane here. Below this particular plane here, and you see what? Q1 and Q2 which are matched. This is common, this is plus, and this is minus here. And so what you can say is, so anyway, so this is there. What you can say is that, this is what we are saying. We can say that this point is also ground. So even though the circuit is not symmetrical, what we are saying is this node is approximate, very small. So this is like ground. So when you look below this particular plane, see, it doesn't matter what is Q3 and Q4 anymore. Why? Because this node is ground and this node is also very close to ground. So when you look below this particular part here, what you see is Q1, Q2, RD, and this voltage will try to make this node positive and this voltage will try to make it negative. Both are equally powerful and therefore this node will become small signal ground still. It's an approximation though, remember, it's not exact. So it's an approximation. I can still make this an approximate small signal ground. Fine. If I do that small signal ground, then what happens is R05 disappears. R05 disappears. Fine. We get this here. But still, the two circuits don't separate out because note that these two are still coupled together, Q3 and Q4. Unlike in the previous case where we had a left half of the circuit, right half of the circuit, and it was straightforward. They're still coupled together. All right. So let's see how to proceed with this. So if I look at now again, we are not going to go ahead and do a hybrid pi and replace it and all that. Our method would be to look at blocks. So we look at as much as possible. So we look at this particular block here, Q2 with a source attached here. And we note that Q2 with the source attached here, we can replace it by a transistor, a current source, which is minus 0.5 GM. GM times this current, this value here. So GM 0.5 VID here. And when you look at it looking from here, from the top, and there's an R0 here. So Q2 with a voltage applied here can be replaced by these two elements here. Okay. Similarly, Q1 with a voltage applied here can be replaced by a dependent current source, 0.5 GM VID, and R0 here. All right. So that's, if you're not convinced, just go ahead and write the hybrid pi model here and see that from this particular point, what is it? You know that from the collector side, you have a current source and an R0. So that's what we have done. Current source and an R0. Okay. So on both sides that are there. Now this R0 gets shorted out, so I don't need to worry about it. R0 ground here and ground here. Fine. Why did I neglect this part? I neglected here also. In this case, of course, it gets shorted out. But in this case, I also neglected R0. Why? Because when you look up, what do you see? You see Q3 with base collector shorted. So what do you see? 1 over GM. And 1 over GM in parallel with R0. It doesn't make any sense to keep R0 here. 1 over GM is so much smaller than R0 here. 2-3 orders of magnitude smaller. So that's why we've neglected R0 here also. Again and again, I'm emphasizing make approximations early. General tendency is to keep everything, make the expression long, and at the end mess it up. Okay, so make approximations as early as possible here. So here also, we neglect R0. We neglect R0, and then this is what we are left with now. Okay? All right. Now, let's see what will happen. So, this current, where will it flow through? Obviously, a part of IN, if I look at the Norton's current, what are the contributions to the Norton's current? Can you see? One is this current. Of course, a part of this current flows here. So that's there. Where else Norton's current would come from? From Q4. Q4 will also give rise to a current. Why will it give rise to a current? Note that this current that you see here, what will happen? It will flow through Q3 and it will develop a voltage here at this particular node. It's a small voltage, but it will develop a voltage here. That voltage will go here to Q4. And what will it do? Note Q3 and Q4 are matched. So what is this voltage due to? Due to this current. This current is causing this voltage here. Now this voltage will cause same current to flow through Q4. It's a current mirror also. Alright. So realize this current will set up a voltage here. As it flows through Q3, what kind of a voltage? So let's see. IN will be equal to, so the point that I'm making is IN has two contributions. One is this current minus 0.5 GMID, and there's another minus 0.5 GMID which is coming over here from this side here, Q4. The total current will become minus GMID. Note that this is 0.5, this is plus. This is plus and this is minus here. So, again, what are we doing? This is 0.5 GMID. This will set up a voltage here, right? The voltage would be 0.5 GMVID multiplied by 1 over GM3. That same voltage will go through Q4 and will cause a current to flow here. And the two currents, when I take a current here and when I take a current here, add them up with the proper sign, we get net current which is equal to minus GMVID. That's the net Norton current that is flowing at this particular point. Okay? All right. A couple of these things, but let's come back to Norton's resistance. Norton's resistance is a little bit more complicated. So, we want to find resistance at this particular node. General procedure is you apply a voltage source Vx and find out how much is Ix. And take the ratio Vx by Ix will give you the resistance here. Note that to find the resistance, we have removed all the sources here. No sources now, and the only source is over here. All right. Now, note that this Ix that you see here, there are two components. As Ix comes here, it will flow into Ix2, and it will flow up whatever is the value Ix4. So Ix will be Ix2 by Vx plus Ix4 by Vx here. So we have to find out what is this Ix2, how much is this? And we have to find out how much is this, Ix4. And take these two and put it over here and calculate what is 1 over R. Alright, let's see Ix2. Let's focus on IX2. So IX2 starts here. This is the collector current. And base currents are small, so these are in active mode. So IX2, the current that starts here flows here. Now once it comes here, note that it has a choice of flowing either through R05 or going into Q1. Where will it go? When you look towards the left here, what do you see? You see into the emitter of Q1, and what do you see? 1 over GM1. So it's a question of 1 over, the current has two options, either flow through R0 or flow through 1 over GM1. And 1 over GM1 is what? Much, much smaller than R05. So this current is not going to go here. It will go here. The same current IX2 that you see here will arrive here. Now note, please keep in mind that these are small signals. So small signals can be positive, negative and all that. Doesn't matter. So if you're worrying that how will it go up into the emitter current is always coming down. That's DC. Okay. So small signal there's no issue with it. Now this IX2 comes here, goes up because this is the emitter current, goes up here, right? Goes up here. Now where will it flow? It will flow through Q3, but with this base and collector shorted together. So how much voltage will develop here? Are you seeing that there is the same current mirror action? It will develop a voltage here at this particular node. At this point, what is the voltage? IX2 multiplied by 1 over GM3. That's the resistance of this. From this node to ground, the resistance is 1 over GM3. So that's the voltage that develops here. Okay? So IX2 starts here, goes here, comes and develops a voltage at this particular point. Alright? So far fine. Let's come to, so this is what we just said here. So we've just followed the path of IX2 starting from here and all the way back to ground. Okay. So as I said, IX2 is what? A part of IX. So it starts from here, goes here, all that and comes back to ground. Okay. Fine. What is the value of IX2? So if I look down here, what is the value of IX2? IX2 will be equal to Vx. And when you look down, what do you see? When you look down, you see Q2. And in the emitter of Q2, what do I have effectively? A resistance with a value of 1 over Gm. Why? Because it is R05. And then when I look from here, it's 1 over Gm. So effective resistance between this node and ground is 1 over Gm. So what is the net resistance when I see from here, from the collector? The net resistance will be R0, 1 plus Gm times Re, whatever is the net resistance connected in the emitter, which is 1 over Gm. Right? So the net current that you see here, IX2 will become Vx divided by R02. This becomes 2R02, so it's Vx by 2R02. That's the net current which is flowing here. But this current IX2, you know that it starts here and goes in this particular manner. But the value of this current is this here, Vx by 2R02. All right, you can stop me at any point if there's a confusion. Okay, so Vx by 2R02 here. So we know that what is this current here? IX2. The next thing is, what is IX4? How much is IX4 here? Okay, let's look at IX4 now. Now note, we have already said what is the voltage at this node. IX2 over 1 over GM3. That voltage we've already developed. So let's focus on Q4. In Q4, there is a voltage attached to the base here, right? And the other thing is ground. And we're not bothering about what is happening down here. So we are only interested in knowing what is IX4. So note, this voltage is VB4. This is ground. And we are asking what is IX4. How much will be IX4? When you have a transistor with this base connected to some voltage, emitter is ground, and note that and how much current would flow here. IX4 will be equal to GM4 VB4. Can you recognize this term? Whenever you apply a voltage between base and emitter, how much current flows into the collector? GM4 times VB4 plus Vx by R04. If what you can do is, again, we are looking from the collector side. Note that when you look at a transistor from the collector side, you have two components of current. One flowing through R0. Between collector and emitter, there's R0. So between collector and emitter, there's an R04. So there's one component, Vx by R04. And there's another which is a dependent current source, which depends on how much voltage you apply here, which is GM4 times VB4. So when you look from here, this is the whole thing is these two current components. And we've already calculated what is VB4. So when we put the value of VB4 here, which is IX2 by 1 over GM3, we end up with an IX4, which is equal to IX2 plus Vx by R04. That's the value of IX4 that we get here. Which is what makes sense here. If you look at it, whatever is the current here, IX2 is flowing here. This is like a current mirror. So whatever current here, IX2 flows here, there's a part IX2 that flows here also. But in addition to the current mirroring action, we've also applied a voltage Vx at this particular node. And that's why this current is there, Vx by R04. So that's why we end up with an IX4, which is IX2 plus Vx by R04 here. All right, let's proceed. So we have IX2, which is Vx by 2 R02. We've already calculated. We have IX4, which is IX2 plus Vx by R04. So let's put all of them together. 1 over Rn was Ix over Vx, Ix2 plus Ix4 by Vx. And when we put it all together, comes out 1 over R02 plus 1 over R04. So finally, when you write 1 over Rn is 1 over R02 plus 1 over R04, it effectively means Rn is the output resistance here, R02, in parallel with R04. So what we have done is, we have said that when we look from here, when I look at this particular node, the Norton's current is equal to minus GMVID. The Norton's resistance is R02, R04, which means that the whole circuit that you see here can be converted into one Norton's current and one Norton's resistance here. And therefore, the net output voltage will be the Norton's current multiplied by Norton's resistance here. And the gain would be V0 divided by VID, and it turns out to be GM1 R02 parallel R04. And the net output resistance looking from here is nothing but the Norton's resistance. When you look from here is R02 parallel R04. So what we have done is we have done a differential mode analysis to find out what is the value of the gain at this particular point, which is GM. And note that both transistors Q1, Q2 are identical. So whether you write GM1 or you write GM2, these are all the same. Okay, so GM1, R02 parallel R04. And note Q3 and Q4 are also identical. Q1 and Q2 are also identical. So you can also write R01 parallel R04. These are the same things. All right, so a fairly elaborate way of calculating what is Rn. Normally, if you go into books, what they would do is the following. If you would look at books, what they'll do is, they'll say, for calculation of R0, when you look from here, they'll say this node is ground. And so when you look down, what do you see? You see Q2 with this particular node ground, so it is R02. And they say this node is ground here, so when you look up, it's R04. And therefore, the effective resistance is R02 parallel R04. So in books, you'll find a very, very simple derivation of saying that, they will take this as ground and make it R02 and up. When you look up, it's R04 and they'll simply write R02 parallel R04. It's far more complicated. The final result is the same. We still get R02 parallel R04. The final result is the same, but that's not how this node is not ground. As you can see here, go back and look at the derivation the way we have done. The current flows here. There's a voltage, the current flows then here. There's not ground. Flows here, sets up a voltage here. It's far more complicated. Sometimes, and this is very common in exams also, students arrive at the right result through the wrong process. Okay? So here also, what you find is, I would say, in many of the books, you get the right result, but the process is not entirely right. Okay, so I've sketched out the complete way of how to get the resistance at this particular point here. And you saw that is depending on the current flowing here, and how that current goes, sets up a voltage here, that causes a current to flow here. A little bit more complicated, but you arrive at an answer which is very simple, which is that the resistance looking from here is resistance looking down, it's like R02, resistance looking up, which is R04, and parallel combination of that. All right, so let's compare the two configurations. If I had a configuration, this one, if I had not used a current mirror action, if I had not used a current mirror action, if I just used a active load, then active load, what would have happened is both sides are symmetrical. It would have broken in half and would have gotten gain as 0.5 GM R02 parallel R04. There was no current mirroring action here, okay? Because once you put it to ground, the left half and the right half are the same, and then it's 0.5 GM R02 R04. Okay, it's just like the earlier case here. All right, as compared to the current mirror, with the current mirror, we get an extra factor of 2 here. So we get GM R02 parallel R06. All right, common mode analysis is even more complicated. And it's more complicated and will not arrive at an answer. So I will not be able to give you an expression for common mode gain. Okay, let's see why it is more complicated. All right, so let's look at the common mode analysis. So we are assuming that, so both voltages are the same, VIC here, and we are assuming that this current source is realized using a transistor. Again, so this is R05. Okay, and so this is the situation we are in. We make it to ground and we put it to ground. So this is the circuit that we have to analyze. All right, let's go there. Okay, so what we are saying is that, remember common mode, how did we do? We said that we are going to split this resistor into 2 parts. A 2R05 in parallel with 2R05. And we said if we take this, the voltage at this particular node is also very small as, comparable to this, then again it's not symmetrical, but we say that this voltage is also small and this is anyway small, and therefore we use symmetry and we break it down into this part. There's a problem. It's not symmetrical. Please keep in mind, it's not entirely symmetrical. Note that this is shorted here and this is no longer shorted here. Okay, so it's not symmetrical, but we are carrying over our notion of symmetry from previous cases, and we're saying, well, let's apply it. Assuming that this voltage is also very small and comparable to VC, then we say when you look down, you see Q1, Q2, below this particular plane, everything is symmetrical. All right, so we do that, 2R05 and 2R05 come here. But they're still coupled together. That's the other complication that occurs here. Okay, so what we need to do is, let's look at the left half plane. Note that the left half plane is not affected by the right half much. Why? Because if I look at this particular node here, the resistance between here and here is 1 over GM. But this node is also connected here. And when I look into the base of Q4, it gives me a resistance between this point and ground as R pi. And R pi is again beta times stronger than 1 over GM. So Q4, this side does not affect this side. Okay? So when I write here the left half of the circuit, left half is Q1, 2R05, VIC, Q3. I'm not bothering about the connection to Q4 because that resistance is much higher. So that's why you see Q4 and all this part absent here. But for the right half, we'll have to bother about the left half. Okay. All right. So this is the circuit that we get here. And it's straightforward to write down what is the gain at this particular point. VC1 by VIC is GM1. What is the net resistance? So this is RC. Net RC is 1 over GM3 divided by 1 plus GM1 times 2R05. That's the standard result that all of you know by now, that when you have an emitter resistance, the overall gain is GMRC divided by 1 plus GMRE. So it's the same result. RC is 1 over GM3, and this is again 2R05. So GM1 R05, of course, is much, much larger than 1. So we ignore 1 here, and we end up with VC1 by VIC, which is 1 over 2 GM1 R05. Okay. So note that both GM1 times R0, if you take the product would come out to be a very large product, maybe 1000. If you take typical values of GM1 and R0 multiplied together, you will get this factor as 1000. And so 1 over 1000, so gain is very, very small here at this particular point here. But note that at every point, we are making approximations. I made an approximation, is not entirely symmetrical, but I still assumed symmetry and broke it down into 2 parts here. So I made an approximation then. Even at this particular point, when I write like this, I'm neglecting 1. And I'm making an approximation. So at every place, I'm making approximations to simplify my result. Alright, so let's go forward. So, left half is done, right half, let's look at it. Right half is here. So VC1 that I just calculated goes here. So VC1 goes to Q4, and then I have Q2, and then I have 2R05, and then I have VIC. This is where I want the gain. My interest is not so much on VC1, but my output is here. And that's where I want to calculate the gain. Now this is where now things get a little bit of a problem. VC1 we just calculated is minus VIC by 2 GM1 R05. Okay, so we know the value of VC1. We know the value here, right here, and we have to find out the net value at this particular point. Now, remember, we are doing small signal analysis, which means it's all linear analysis. It's a linear circuit. So what I can do is, I can first find out V0 due to VIC, and then find out V0 due to VC1 and sum them up, and I'll get the final answer. Okay. Now, a little bit of, just to remind you of a few results. Okay, these, just to refresh your memories, everybody knows this result? Common emitter amplifier within RC, except that note, I've included R0 also. This is general, we've been neglecting R0, but let's keep it. V0 by Vi is minus GM RC parallel R0, okay? Do we recognize this? This is NPN, and this is PNP. Same, Vi applied. Collector here, again minus GM RC parallel R0. Okay, so now, can you see this part here? Can you see the result for this one? Compare this with this. GM4. What is this RC for this transistor? RC for this circuit here. RC for this circuit would be resistance looking down, right? Resistance looking down, so I put R down, whatever it is, for a moment. And R0 is what? Resistance looking up, which is R04. So everybody agrees this is fine? Minus GM4, because why GM4? Because I've applied the signal here. Minus GM4, R04, parallel R down. It's the same expression, except that RC is down here and everything below is R down here. Now, when you look at R down, what do you see? When you look at the collector and there's a large resistance connected in the emitter, what will be the net resistance R down? R down will be equal to R02 multiplied by 1 plus GM 2R05 parallel R pi. So again, if you look at it, R down will be very large. Will be very large, so we can simply write down minus GM4 R04. Okay? Again, I'm emphasizing, I'm making approximations, okay? A lot of approximations, as you can see here. I'm neglecting this. So I get minus GM4 R04. Alright, so the effect of VC1 at V0, we have calculated. Minus GM4 times R04. Okay. Again, a few results here. If I look at, alright, minus GM4 R04 here, and then we have put the value of here VC1, we have put the value. VC1 we had already calculated, and let me see what we are doing. All right, so this is what we just obtained. Now let's look at V0 by, sorry, yeah, this is what I'm missing. V0 by VIC. I had the result before these schematics, so I was getting confused here. All right. What is now, so we already calculated V0 due to VC1. Now V0 due to VIC. Can we see this result? This result would be what? Note that this result is a transistor with a resistance in the emitter and with a load resistance of how much? Load resistance of R04. So what will be the net value? GM2 divided by 1 plus GM2 times RE. RE is 2R05 multiplied by RC. RC is R04, but we've also taken, normally, remember the gain is RC parallel R0. So the gain at this particular point is the net resistance here is R04 in parallel with whatever is the resistance looking down, which is R down here. V0 by VIC. will be GM2, this transistor, divided by 1 plus GMRE. Alright, so this is nothing but GMRE, RE is 2R05, multiplied by the net resistance at this particular node. The net resistance is R04 parallel R down. And R04 parallel R down, we are again saying R down is very large, so it's R04. So the net V0 by VIC comes out to be minus R04 by 2R05. It's the same thing. No, so, okay, go back and see this equation. When we say, let's look at this. When we say RC parallel R0, right? What does it really mean? When you look at this node, what is the resistance looking up is RC. What is the resistance looking down? It is R0. So when I have something connected here, then it is, the more general expression is, at this point, what is the net resistance? And you have to look at resistance looking up and resistance looking down. So in this case, it happens to be R0. In the next case, it happens to be, in this case, it happens to be resistance looking up is R04. Resistance looking down, well, I put R down. Okay, R down, which is very large. Okay, R down very large. So I've neglected R down and written only R04. Okay, so we end up getting the V0 by VIC is R04 by 2R05. So we've obtained both. So now what we do is we have obtained V0 due to VIC and V0 due to VC1, and let's add them up. Okay, let's add them up. So when we add them up, the two expressions here, V0 due to VIC and V0 due to VC1, what we find is that the two expressions cancel each other and we get 0. The two expressions, VIC and VC1, the two of them that I calculated, and I put the expression for VC1 is VIC, we had already calculated here. When I put them together, I get 0. My output voltage turns out to be 0, which says common mode gain is 0. So at this point, I have to pause. Why? Because we've made a series of approximations. We made a series of approximations, and what is happening is, after making those approximations, I'm getting 0. It's not going to be 0. So what it means is that I have to do a very accurate analysis and not neglect anything. So there are places where, as I said, I'm constantly telling you, make approximations early and work it out, right? Simplify your expressions and get it out. Here is one place where our method breaks. Early approximations, neglecting things and all that. Why? Because the two terms are actually canceling each other. The gain that it comes from here to here and the gain that comes from here to here, the two terms, they are canceling each other. They are opposing each other. And when you have two terms which oppose each other and you start getting 0, you have to take a pause and say, well, I don't have an exact expression here and I don't have an exact expression here also. Right? So I have to go back and do a very accurate analysis. And that's where very accurate analysis, which means that I don't have to take symmetry into account. It's not symmetrical, and a lot of approximations that we have made, I have to take the exact expression for R down. And all of that, then we'll get into trouble. So for those of you who are brave, can do an exact analysis. And if you end up getting a nice expression, please pass it to us. I'll show it to, I'll show in the next class. So I gave up at this particular point. I didn't calculate. Okay. So I said, that in this case, the expression, whatever it is, so I'm not giving you an expression now. All that I'm saying is note that there is a cancellation process, which means that the common mode gain is likely to be very small. How small? Well, we'll have to use the simulation to get an idea of how small. But as I said, fundamentally, it's not a difficult thing to do. You have to keep all the terms, becomes a long, complicated expression. And somebody please try it out and see what you get, okay? So I'll give you from simulation then. I'll give you an example from simulation, okay? So here is my amplifier, the small signal analysis that I was doing, okay? So common mode, small signal analysis. So if I apply 0.5 here and I apply 0.5 here, okay? So when you don't apply anything 0 here and 0 here, obviously there's no voltage here. So when you apply 0.5 and 0.5, you get minus 135 mu, and you get here at this node, sorry, this should be up, you get minus 4.95 milli. Now note at this point our formula gives VIC by 2 GM and all that, we derived this, it gives minus 0.13 milli. So this node voltage we are able to get very accurately. Okay, our calculation at this point is fine. At this point is where cancellation was occurring and we were not able to get the answer. Okay, and this one gives you, this is simulation, so this gives you minus 4.95 milli. So if you divide this by the common mode voltage, you get ACM, which is 0.01. You can see, because we had made approximations and all that, we were saying ACM equal to 0. ACM is not 0. It is 0.01. Okay, so there is an expression. If you put in the values, you should get values equal to 0.01. All right. So, so that's where it is. Now, note the value of the, let's see here. Look at the two cases here. This is the our differential pair with current mirror load, and this is our differential pair with a normal active load where we had a bias here, where we had a bias, and so I'm putting exactly the same condition, 0.5 here, and at this node I'm getting a gain, we just said minus 4.95, so we got a gain of 0.01, and at this stage here and here, this is a symmetrical circuit, and we get a gain of 0.01 here, we get a gain of 1. This circuit I can easily analyze because it's symmetrical, it's exactly the same analysis that we have done earlier, where all that we have is, instead of RC, we have R03. That's all. So for this, I can actually calculate and show how much is the gain here. And the gain is equal to 1 here. The gain is equal to 0.01 here. So the point that I'm trying to emphasize is, although we could not calculate the gain, exactly what we got was a gain which is very small, 0. That was our prediction, that very small gain here, which is what we indeed see, that the gain here is 0.01 as compared to a circuit like this, which is gain is equal to 1. Okay. So common mode gain is much higher in this. Okay. So as a summary, what did we find for this this amplifier here? IN, RN, of course, all of these we found. ADM is GM1, R02 parallel R04. R0 is here. ACM, I've left it blank. CMRR, I've left it blank. We can't calculate ACM, and then obviously we can't calculate CMRR as well, because we don't have an expression, so we can't, all that we can say is small, and CMRR is high. That's all we can say here at this particular stage. Simulation gives us, so let me summarize, what does simulation give us? Bias point is fine, IE is 2 milliamperes, ICQ1, ICQ2, 1 milliamperes here. GM1, R02, we know how to calculate these. ADM, minus 1.9 into 10 power 3. RID, 5.2K. We know how to calculate each one of them. ACM, I put in red through simulation, minus 10 to the power minus 2, 0.01. RIC is 1.14 mega ohm. CMRR, 1.9 into 10 to the power 5. So, in terms of overall performance, you see a very good result here. Very high differential mode gain, very low common mode gain, very high CMRR value. Okay, so as a differential amplifier, it works very well. Very, very high CMRR, 100 dBs, and very good differential mode gain. So that's why I said that this is one of the most popular amplifiers when you want to implement things monolithically on a piece of silicon. So I've shown you here a NPN current mirror, NPN differential pair with the PNP current mirror. You can of course do a complementary in the sense that you could take a PNP differential pair with an NPN current mirror. You can just flip it and you'll get another configuration. Okay. All right. Comparing this with this one. Comparing a simple active load with a bias and versus a current mirror. Okay, if we compare the two, we've already seen this bias point is extremely sensitive. And we need an additional circuit to bias it, and the bias point is very sensitive. Here, stable bias point. Gain for this particular circuit, 0.5 GM1, R02 parallel R04. Gain here is GM1, R02 parallel R04. Twice the differential mode gain here. Common mode gain is R03 by 2 R05. We can calculate here. We couldn't calculate, but the value here is maybe 100 times smaller. So when I compare this circuit with respect to this particular circuit here, and as I was saying, the difference that one single wire can make. All that we have done is, instead of applying a bias here, if you think about it, just connected it here. Right? And the differences that you get here. You don't need a bias circuitry. You get a doubling of gain, and you get ACM, which is much smaller, and common mode rejection ratio, which is also much higher. All right. So as I said, it's seldom that we use an amplifier at this of this kind here. Now, there's one point that I want to make here before we stop our discussion. I've shown you here that the gain of this particular circuit, if you go back, what we just said, the gain here is the Norton's current, which is GMVID, and Norton's resistance R02 parallel R04. And we had gone through a complicated route to arrive at this particular expression. But as I said, the result is the same as if you assume this to be ground. If you assume this to be ground, then the result is the same, that what is the resistance looking down? What is the resistance looking down when you assume it to be ground here? So is R02. And what is the resistance looking up if you assume it that this point is also ground here, is R04. So although the process is not the same, but the result is the right one. Okay. So now if you had a more complicated differential pair, say more complicated differential pair, suppose I had put here a resistance in the emitter, a resistance in the emitter of Q2, a resistance in the emitter of Q1, or I put something else in Q4 here. Are you going to go through the whole route? Well, that's the correct way of doing it. But the result is going to be the same. So what you can do is, when you analyze, what you can do is, you can say, well, what is the resistance looking down? Whatever I put here. And you put this point here, the common point, to ground. Okay? Whatever is the resistance looking down. And whatever is the resistance looking up, on this side, you put it to ground. And the final answer that you will get is the same that you get through more complicated analysis. All right. So when you have to work out in exams or elsewhere or whatever, resistance looking down at this node, resistance looking up at this node. That's all you need to do. You don't need to do that long analysis. Okay. So wrong process, maybe not a right process, but right result. Okay. So I'm advocating something, using a wrong process to get a right result. But what I'm advocating is not so much as a wrong process. I'm saying a simplified process which happens to work. Okay, happens to give you the right result. All right. So with that, we come to the end of our discussion related to differential pairs. There's one thing that we have not done. All along we've taken a differential pair like this, and we have applied input voltage here and input voltage here, and we've said input voltages are small, and therefore we can do small signal analysis. What if the input voltages are not that small? What if they are large? As a specific case, we don't have that much time, but as a specific case, think about the following. If I have ground here and I have ground here, both sides are ground, then whatever is the current here, 2 milliamperes here, one will flow here and one will flow here. But suppose I put here ground 0 and I put here 1 volt. Think about it. 0 here, 0 at this, V in 2 is 0, and V in 1 is 1 volt. What will happen? Well, what is VID? If this is 1 and this is 0, VID is 1 volt. 1 volt I cannot apply small signal. VID has to be comparable with thermal voltage VT. So I can't apply that. So that is out. I can't do small signal. But when you apply 1 volt here and 0 here, if you just think about it, 1 volt here, which means that the forward bias on this transistor is much higher than the forward bias on this transistor. Because note that 1 volt is applied to the base and 0 is applied here. Forward bias of Q1 is much, much higher than Q2. In fact, note if you have two transistors, Q1 and Q2, if the forward bias of one transistor is KT by Q higher than the other transistor, KT by Q only, current goes exponentially with voltage. So the current becomes E times 2.7 times higher than the other one. So when here I'm talking about when you apply a large voltage, 1 volt here and this one here, what would happen is whatever current is flowing here, 2 milliamperes, the entire 2 milliamperes will now flow through Q1 and nothing will flow through Q2 because the forward bias on Q1 is so much higher than Q2. Entire current will flow through Q1. Nothing will here. On the other hand, if I have this current here and you apply a large voltage here compared to this, the entire current will flow through Q2 and Q1 will actually go into cutoff. So what you find is that this current that you see here, yes, when you put 0 and 0, the current equally distributes between Q1 and Q2. If you apply a large voltage here, you can get most of the current flowing through Q1. If you apply a large voltage here, you'll get most of the current going through Q2. So what I'm going to do is in the notes here, I'm just going to, it's a simple derivation here which tells you how much of current flows in Q1 and how much it flows in Q2. So I'll end our discussion at this point. You can take a look at it itself. IE is made up of the sum of the two currents, IC1. We've already seen how it relates to VB1, how it relates to VB2. And we can get how much current flows in each one of them here. Okay. So let's stop here. Next lecture is on op-amp now.